All right, we're back. Let me know if you're out there. Checking up on the second half of trees today. We'll get into finishing this up and working on AVL trees as well. We left off with this exercise of how to find the node with the smallest key. And this one is pretty straightforward if you think about where the smallest key exists in a binary search tree. First of all, it has to be a node that has no left child. Because of the binary search tree property, anything that's in the left subtree of a node has to be less than that node. So by induction, if I've got a node that I think is I guess that wouldn't be induction, that would be the contradiction proof. If there's a node that I think is the smallest node, and then I go to its left subtree, I've found something that disproves the fact that it's the smallest node. So I'm looking for a node that has no left child. It may have a right child. It may be a leaf node, but that's not important. It is going to have no left child. So all we have to do is start at our root and keep going left until we can't go left anymore. The solution that we saw for that was this one here that is iterative there in lines 5 and 6. As long as x has a left, we set x equal to x left. That'll get us there. So you could have also written this as a recursive function to make sure that you can understand how this works recursively and iteratively, and understand how the tree traversal and manipulation works in general. I strongly suggest that. Either way, you should be able to get that down to an average case complexity of log n and a worst case complexity of n. This is completely dictated by the height of the tree, because on average it has to do with where that leftmost item is. What about removing a node from a tree? So far we've looked at building these things, where to insert things, where to find things, but what happens when something needs to be removed from the tree? That's our next step. So in our binary search tree, every node has the possibility of no more than 2 children, which gives us 4 different possibilities when we're trying to remove a node. The first of which is pretty trivial. If the node that I'm removing has no children, it's easy to see how removing that node is just about done as soon as we think about it. When a node has a no left child or no right child, if you think about the way the binary search tree property works, we can easily replace the node that we're deleting with the child that exists. So if the node has only 1 child, we can replace that node with the child upon removal, and that still keeps the rest of our tree in a fully compliant binary search tree mode. It's got our invariant and it maintains that. Now where it gets a little bit more challenging is when Z has 2 children, and Z is the node that we're removing. So if we're removing a node, it's a little bit harder to figure out, how do I replace this, or what do I put in there to replace this so that my tree doesn't fall apart? If it's got 2 children, I can't necessarily pick 1 because that child may have 2 children as well. So I've got to figure out how to go down from 2 to 1 to make that work. And the full algorithm of this is discussed in CLRS 12.3 if you've had a chance to check out that text. But we're going to go over it here in the slides. So let's look at these things. These are diagrams from CLRS. We're looking at removing the node Z there, and what's coming from Q is just some pointer that maintains where we are. So that could imply that we're removing the root. That could imply that we're removing something that's not the root. What we're concerned about here is, as we're removing Z with no left child, we see that nil pointer there. That's this particular illustration style, calls them nils. We can call them nulls. It's the same thing. So Z has no left subtree. And then below R, we see these dotted lines that tell us that there may be any number of items below R. We don't really care. So that's information that we don't have, and it turns out that doesn't really matter to us. But if Q could be pointing at Z when Z has no left child, I can simply remove Z and have Q point at R. So now you see there's just a single pointer manipulation, well, 2 pointer manipulations. We're going to move the Q pointer to Z's child, and then delete Z and set Z's child pointer to null pointer, or clear that thing up. So that's easy. That's the easy case number one. The easy case number two is just the mirror image of this. When Z has no right child, we can easily replace it by Z's left child. And so we see that here. And if you think about the way that this works, whatever was pointing at Z, wherever Q is coming from, is if Q is the root, then it's easy to replace Z just by removing that topmost node, and there's no problem. If Q is not the root, if Q is pointing to Z, regardless of if Z is Q's right child or Q's left child, we can think about how that should go. So if Q is pointing to Z and it's a right child, then everything that is coming from where Q is less than those values. And since everything in Z's left child is greater than Q's right child and also less than Z's left, we can upgrade that with no problem, because all of the things in Z's left are still greater than whatever Q is, because it's in Q's right subtree. The same is true if Q is a node that's pointing to the left to find Z. That means that everything in Z is less than what's at Q, and since L is less than Z, with that transitive relationship is maintained. Q is greater than Z, Z is greater than L, therefore Q is greater than L, and I can easily replace it. So that's our two easy cases. The hard case is next. When there's two children, we have to come up with some way to combine this tree with two of them. The observation that we're going to use here is that everything in the left-hand subtree, because it's less than the root, has to be also less than everything in the right-hand subtree, right? Remember, the things in the right-hand subtree are not less than the root. So if all of them are greater than or equal to the root, they all must be greater than everything in the left-hand subtree. So to implement this deletion, what we're going to do is I'm going to transport the smallest right-hand side node. So let's think about that. A right-hand side node is always going to be not less than the node itself. So it's not less than the node itself. So at the very least, it could be equal to the node itself because it's in the right-hand subtree. If it's not quite that small, it has to be greater than the node. That means it's going to be still greater than everything in the left-hand subtree. This is going to be great. So if we find that smallest right-hand side node, it's got a name. We call it the in-order successor, and that's just putting some words together that you should be able to handle. We talked about the in-order traversal, and we know that in a binary search tree, the in-order traversal gives us sorted data. So the in-order successor is the item that comes right after the node if I were to do an in-order traversal. So the node that follows this, that is the smallest node in its right-hand subtree. So we already figured out how to find the minimum element. All we need to do now is jump over to the right-hand subtree and then find the minimum element over there. That's pretty easy. The thing about that is when it's the minimum element on a side, we know that it has no left-hand subtree. So that I can easily promote that thing to the deletion spot, and I can pick up any left tree that exists on the original nodes, or the original deletion node. All right, let's see how this looks in pictures. So here we have V, which is the item we're going to remove. It's got some left-hand side, which is this cyan triangle, meaning we don't know how many items are over there, but there's something there. The same is true on the right-hand side. There's some triangle over there, that's the magenta one, that says that there's something there. And then the 0th node, that's the one that's the smallest node on the right-hand side, is somewhere over there. And in the picture, it's shown to the far left and at the bottom, which is where the smallest item in that right-hand subtree has to be. So if I replace V with that 0th item, that smallest right-hand side item, we see that its final position looks great. On the far right there, we've got the smallest right-hand side element pointing to its right, to all of the other right-hand side elements, which means all of the other right-hand side elements have to be not less than that element, which is everything on the right side is greater than or equal to that smallest element, which makes it fit. That's great. That smallest right-hand side element, though, even though it's in the right-hand side, still has to be larger than every left-hand side element, so that fits perfectly just as well. So if we can find that in-order successor here and replace V with it, then we can quite easily delete V and still have our tree in perfect working order. This is a piece of code that does a really nice version of it. It's kind of hard to track because it is recursive and it uses a recursion quite smoothly. It uses a recursion to both look up the item and to do the replacement. It's really a piece of elegant code here, but it's hard to think about. So we've got this binary tree remove, and what we're doing is we're passing in another pointer by reference to the tree. That's where we're starting at. And then we're passing in some value. This is the one that we're trying to remove. So we've got a basic pointer and the value that we need to find in order to remove it. This couple of pointers that we use here, first one that keeps track of where we started, that's the node to delete. For starters, we're going to point it to the top where we were just handed off. Then we're going to try to move that node to delete down until we find what we're looking for, and then delete from there. We've got another pointer to hold the in-order successor when we're ready to delete something. If we've got two children, we'll track down, find the in-order successor, and use that to replace the node that's going to be deleted. First step, though, however, is to find the thing that we're trying to delete. This, since it's a recursive function, and we may be asking to delete something that doesn't exist, we need to have our base case, right? We're passing that pointer by reference because we may need to change it. Right, if I've got a copy of the pointer and I say, well, set this pointer to null pointer, that sets my copy of the pointer to null pointer. It doesn't set the pointer that was sent from the calling location. So whatever function called remove, it wants the pointer there to be changed. It doesn't want to send a copy of that pointer into the function and have that moved around and not affect what's going on outside of the remove function. So that's why we send the pointer in by reference, because the function needs to be able to modify the pointer at the calling location, not just within the called function. All right, so our recursive nature here means we've got to have our base case first, and there it is. If that tree is a null pointer, then just be done. We've either started out trying to remove something from an empty tree, which is okay. We don't want to die there, so we've got a protection. Or we could be calling remove here again in lines 10 and 12 while we're on the hunt for the value that we're trying to delete. And if the value doesn't exist, we find a null pointer before we find anything. And so we need to be able to get out of that. So that's what the rest of this does here. In the else if in lines 9 and 11, it says, hey, if the value that we're trying to find is less than what I'm looking at, go left. Otherwise, if the value that I'm looking at is less than the value I'm trying to find, go right, right? So that catches my less than over here and my greater than over there. So the final else here on line 13 that goes to the next page is what? That's when the value that I'm looking at is equal to the value that I'm looking for. So this is where we found the location to delete. So in 7 and 8, we get out of the base case. 9 and 10, 11 and 12, that's furthering our search into either one of the subtrees. And then 13 is where we kick into tree must be pointing at the value that we're trying to delete. So as we move to the second slide, we now have tree pointing at the value that needs to be deleted. Here in lines 15 and 19 is where we identify the fact that this node has only one child. In 15 it says if tree left is null pointer. In 19 it says if tree right is null pointer. This allows us to do our one child delete. You say, well, what happened to the 0 child delete? Turns out that the one child delete here in 15 also picks that up. Because if tree left is null pointer and tree right is null pointer, we still do the same thing. We're just going to delete that node, which is here in 17. And as we promote the tree to be pointing at trees right, which was already a null pointer, all we're doing is a real clean removal of a node with 0 children. So 15 through 18 handle both the zero child case and the right child only case. 19 handles the left child only case. And then we move on to the last page, which is where we're in this last final else. And this else from 23 on down to 34 handles when we've got a node that we're removing. We've already identified it. Tree is pointing at it. And it has 2 children. So let's find that in-order successor. It's pretty easy. We're just going to jump once to the right into that tree's right-hand side. And if that's not a null pointer, because it could be a null pointer, it could be empty there. Oh no, sorry, it couldn't be empty. Tree right can't be empty. We've already determined that from the previous slide. So that's why in-order successor can easily jump right without checking. Then we do need to work our way to the left, right? And that's why we keep checking here. If the in-order successor has a left, then we're going to update the in-order successor by taking that left. So this setup here in 25, 27, and 28, just jog once to the right and then go left as many times as it can until you hit you hit the bottom node that has no left subtree. So now with in-order successor pointing at the thing we're going to replace with, and tree pointing at the thing we're going to delete, we can do the easy thing, because now we're at a situation where we're deleting an item that has only it has to be replaced, and we're going to replace that here. We see that in 31. It's a node to delete's value. We're going to set that equal to the in-order successor's value. So that's taking that thing from the bottom of the tree. So in this case, what we're going to do is we're not going to move the node. We're going to change the value of the node. And if you wanted to do this the other way, where the nodes had to be protected, so you couldn't delete a node unless that node was going to be the one that was deleted, this version does a value swap. So it takes the value out of the in-order successor and puts it at the node that's going to be deleted, and then it just calls remove on the in-order successor. So it recurses into itself to handle that cleanup, because remember now, we know that the in-order successor has at least one null child pointer. It has to have a left child null pointer. It may have a right child null pointer. In that case, remove cleans it up pretty easily. But even if it has a right child pointer that's not null, remove cleans it up pretty easily. So remove here is used pretty nicely, right? We saw remove being used on the first slide to do the searching. We see remove being used on the third side to actually be doing the removal of the partial there, and the rest of this works out pretty nicely. So it's a nice piece of code. As I said, it is recursive with the remove there multiple times. Make sure you understand it. Walk your way back through it. If you want to get really tricky, try to find a way to write single function remove iteratively. Great work. Here's my BST summary. Each node has at most 2 children, a left and a right. Some implementations you may use a parent pointer. We did that in the pairing heap. But in the BST, and not in the pairing heap, we have to make sure that this BST property is maintained. And that one we've looked at, we said everything in the left is less than the root, and everything in the right is not less than the root. We'll call that greater than or equal to the root. The modification of nodes was pretty easy when we're working externally, and the more internal the node became, the more complicated it got. So that was something that we learned about. And in general, we know that our BST operations now are totally based on the height of the tree. So average case, we end up with a height somewhere between log n and 2 log n. And the worst case is when we've got a stick and we can have things as a linear search. Then we've got a tree that just goes straight down, and we spend n time on that. That's our binary search trees. We're happy about them. They do good work for us. Next up, we're going to talk about AVL trees. An AVL tree is a type of binary search tree. So in terms of the way that our set notation works, we've got all graphs out here. Then some trees are graphs, so all trees are inside that graph domain. And then some trees are binary trees, and that's farther inside the tree domain. And then some binary trees are binary search trees. And then we've got this AVL tree that we're going to talk about now that says all AVL trees are BSTs, but not all BSTs are AVL. So as I move farther inside the BST domain, I will find that some BSTs are AVL trees. So an AVL tree is a self-balancing tree. One of the things that we liked about the binary search tree was that all of the operations that we looked at were based on the height of the tree. And in an average case, our tree stayed nice in the log area. But our worst case allowed things to go back to linear. So an AVL tree, a self-balancing binary tree, what that does is it maintains the binary search tree property, but it keeps it from turning into a stick. So as operations are performed on the tree, whether they're insertions or removals, the tree balances itself so that it doesn't get out of whack. And there's a few different types of self-balancing binary search trees. There's red-black trees, and there's AVL trees. But we're going to take AVL trees because they're fairly easy to understand and talk about. They are not quite as useful as a red-black tree. Red-black trees are a bit more efficient than AVL trees, but they're much more complicated. We could spend an entire day trying to talk about red-black trees, and this was done to me while I was in school. They talked about red-black trees, and I remember them spending the day, and I still walked away not understanding what was going on. So AVL trees are a bit simpler, and they show what we're trying to show you, that a tree can be made to be self-balancing. In the end, there's very little chance that you're going to be implementing your own self-balancing binary search tree. You're probably going to use the one in the library that you have. So the STL is generally implemented with a red-black tree, but it's not important for us to do that implementation. It's not as important as it is for us to just understand how a tree may self-balance. So the name is based on the people who worked on it, Allison Velsky and Landis. That's where the A, V, and L come from. It starts with a BST, so as I mentioned, all AVL trees are binary search trees. And then it adds this height balance property here. And the height balance property is easily stated as every internal node of T, the heights of the children of that node differ by at most 1. That's fairly well balanced. So you can see how this would prevent me from having a stick, right? If I've got one child here, if I've got a root here, I can't have 4 children on this side and no children on that side. That would violate my height balance property because I'd have a subtree of height 4 and a subtree of height 0, and those differ by more than 1. So the height balance property is going to prevent that from happening. And to do that, as we modify the tree, we're going to learn about how to apply rotations. And what a rotation does is it takes those things and looks at the children's heights, and if they differ by too much, it moves a few nodes around until we've got a tree that's more balanced. And as long as that's done every time, and what we're going to do is we're going to keep the binary search tree property as an invariant, and we keep the height balance property as an invariant, then we have our AVL tree has to be a binary search tree that is never more than log n tall. And that makes all of our worst case be as good as our average case. And that's amazing. We talked about tree height. Tree height is measured from the bottom up. So as we put in some new node, it's easy to say how I can update heights above that node. If I put in some new node as a leaf node, it's got to have a height 1. Every leaf node has a height 1, and every time you insert a node, you're inserting it as a leaf. So there, it's easy to say I'm going to work my way up from here, trying to make sure that all of my parents are well balanced. You say, well, how do you work your way up in a binary search tree unless you have a parent pointer? I mean, you said we weren't going to use parent pointers very much at all. And we still can get away without doing this without a parent pointer because we have to look at the recursive nature of this tree. If we use some sort of recursion to find the location where I'm going to insert, I've called it on this node, and then I call it on its child, and I call it on its child and its child there. When I find the location where I'm going to insert it, I still have to return back up through the chain of parents that found that location. So this gives us the ability to traverse upwards in the tree even without parent pointers. Our height is independent from our depth. Remember, we measure depth from the root, and the depth is not really going to help us in this balancing here, so we can completely just leave that out of it. We do have this recursive formula for height, and we saw it on day one here. We said height of an empty tree is 0, then height of any node is the maximum height of all of its children plus 1. Great. Now we know how to calculate tree. So height of the tree. So let's look at some examples here. Is this an AVL tree is the title of this slide. And this one is just having a look at the height balance property. And it's restated there. For every internal node V of T, the heights of the children of V differ by at most 1. So tree 0, that's an empty tree. It's easy to see that the height there is balanced. I have no internal nodes, so I can't have any internal nodes that are unbalanced. Remember, it's only internal nodes having heights of their children that differ that give us a problem. So here in tree 1, I've got no internal nodes again. It must be balanced. Tree 2 has an internal node. 5 has a left child, but has no right child. Since that left child is a leaf node, I can say that the height of that left child of 5 is 1. The height of the empty right subtree of 5 is 0. So 1 and 0 differ by only 1. So that then is balanced. How about this next tree, tree number 3? Well, it looks like as I start from the top, 5 has a left subtree of height 2. This 2 has a subtree of 3 that's of height 1, so that puts 2 at height 2. So 5's left subtree is height 2. 5 has an empty right subtree, so that's height 0. So now I'm comparing 2 to 0, and that is not balanced. So that I can say is not an AVL tree. It is a binary search tree, but it is not an AVL tree. How about as we move on? Tree 4 here. Now as I look at the root node has a subtree on its left of height 2, a subtree on its right of height 1, so the root node is balanced. Any leaf node is balanced, so I can say that that 7 on the far side is balanced. How about 2? Is 2 balanced? Well, 2 has an empty left subtree and a right subtree of height 1, so there's a 0 on the left and a 1 on the right. So 2 is balanced, 5 is balanced, 7 is balanced. All of the nodes in the tree have to be balanced in order for the tree to be balanced. I'm going to say that this tree number 4 is the balanced tree. We see that it's not complete. That's okay. It does not have to be complete. The tree has a blank spot here on the left. The tree next to it, tree number 5, what about that one? Same thing applies here. I don't have to have a complete tree. I don't have to fill an entire row before I move on. But as I evaluate my way from the top to the bottom, I see that 5 has a left subtree height of 2 and has a right subtree height of 2, so 5 is balanced. Then 2 and the trees rooted at 2 and 7 are kind of mirror images of each other. They both have one subtree with a single child and a null on the other side. So 2 and 7 are balanced. 3 and 6 are both leaf nodes. They're balanced. All 5 of those nodes in tree 5 are balanced. Therefore, tree 5 is balanced. How about tree 6? We've added a little bit more here. Tree 6 at node 5. It's actually balanced. Its right subtree is height 3. Its left subtree is height 2. They differ by at most 1. That's okay. 5 is balanced. As I work my way to the left, I see 2 has a subtree on the right of height 1 and an empty subtree on the left. So 2 is balanced. 3 is a leaf node. 3 is balanced. Half of this tree is completely balanced. What about node 7 there? Well, node 7 has an empty left subtree and then 2 items stacked on top of each other in its right subtree. So the height of the right subtree of 7 is 2. The height of the left subtree, which is empty, is 0. We are not balanced because of what's going on there at 7. If you look past 7, you see that 9 and 8 are actually balanced. So balance is something that can happen everywhere. It can also be thrown off just about anywhere. I mean, we can't throw off balance, obviously, in a leaf node because they always are balanced. They always have a height of 1. But any other internal node has the possibility of being imbalanced. So we have to find where that is when we're doing this. And the good news is that's pretty easy because if we start with an AVL tree, which we saw that in tree 0, there was nothing in it. It was balanced. or that was tree 1, right? Then tree 2 with the single node, same thing. It's balanced. So as I'm adding these nodes, I have an AVL tree. It's only when I add something to like a tree like 5, if I could have added something else below the 6, then I would have unbalanced that tree. So if I'm checking as I make the modification, I know right away when the thing becomes unbalanced. So there's tree 6, not an AVL tree. Here's our proof of how the AVL tree works. And we're not really big on proofs in 281. We like to get things set up, make sure that you've got a basic understanding of how the proof should work, and we wave our hands and point fingers at the 203 crew. So you can go talk to them if you want some in-depth work on how this proof works. But I'll give you the basics of it, and it should make it fairly clear. So we've got H, which is already the height of the tree. We've talked about in the past. This new notation that we're coming up now with is N of H. And this is the hardest part of this thing to grasp, I think, so far with students. N of H is the minimum number of nodes in an AVL tree of height H, as it says there. So if the height is H, N is the minimum number of nodes that I can make a balanced AVL tree with that height. Our base cases are pretty easy. Obviously, the minimum number of nodes in a tree of height 0 is 0 because it's an empty tree. How about when the height is 1? Well, there's only one way to get a 1 height tree anyway. That's with the single nodes. So the number of nodes in a tree of height 1 would have to also be 1. So there's a couple of base cases. Because this is a recursive thing, now we're going to jump to the recursive step. So for any height greater than 1, we can say that the AVL tree has a balanced AVL tree, has a short side and a long side. Why does it have to have a short side? Because remember, we're looking for the minimum number of nodes. If both sides were the same height, I would have more nodes than I needed. I could take one off here and I would still be okay. So as I set an AVL tree up, an AVL tree with a minimum number of nodes for a given height has to have a long side or a tall side and a short side. In that case, then, I can say the total number of nodes has to look like something where I've got a node at the root and then an AVL subtree of height h minus 1, that's the tall side, and then an AVL subtree of height minus 2. On our picture over there, we've got 5 at the root. We've got a tall side that's got 2 and 3 underneath it, and then a short side that has 7 underneath it. 2 and 3 give me a nice balanced AVL subtree. 7 is an AVL subtree. 5 is an AVL tree. So you can see that for any given height, I can say that the total number of nodes has to be made up of the root, the short side, be it left or right, and the tall side, be it right or left. So here I say that my total height for anything greater than 1 looks like 1, the root, plus the number of items in the tall side, n of h minus 1, and the number of items in the short side, n of h minus 2. Those are the things that make up the total number of nodes. Great. Let's see where that takes us. Now, n of h minus 1. H minus 1 is our total height is h. So h minus 1 is the one that's just a little bit shorter. So that's the tall side. H minus 2, that's the short side. And it's not too hard to see why there should be more nodes in the tall side than there are in the short side. It's taller. So I can say that the number of nodes, n of h minus 1, has to be greater than n of h minus 2 because there's more nodes in the tall side. In that case, I can say that because n of h is the sum of n of h minus 1 and n of h minus 2 and 1, that n of h has to be greater than 2 times the small side. Okay? Small side has fewer items than tall side. Total is small plus tall plus 1. So I can say total has to be greater than small plus small. You got me now? This is a 281 style proof. Talk about some things and wave some hands. But the number of items has to be greater than the total number of items in the short side, because there's got to be a tall side. So we can simplify that a little bit and say n of h is greater than 2 times n of h minus 2. Then we wave our hands here. We get into the proof by induction thing. We find out that n of h has got to be greater than 2 to the I times n of h minus 2I. So this is the induction part as this tree grows up, and then we take that into a closed form solution and then find out that n of h has to be greater than 2 to the h over 2 minus 1. If you want more proof help, talk to the 203s. I'm telling you. But this leads us to something that I can then get to a place where I can take a logarithm. I've got 2 to the h minus 2. So it turns out if I take the log of those two sides, I end up with h being less than 2 times log of n of h plus 2, right? Like I said, you're not going to be responsible for this on the exam, but I wanted to give you a feel for it. After we've taken this closed form solution, we find here that h has to be less than 2 log n. That's the rough there, right? So we can say that the height of the tree, when it's an AVL tree, because the things that we've talked about so far, has to be log of n if it's an AVL tree, period. It has to be somewhere between n and 2 log n, and that's great. Sorry, I take that back. It has to be somewhere between log of n and 2 log of n. There we go. All right, so as we look at our AVL tree algorithms, we're doing pretty good. Search is the same as a BST because it is a BST. Sort is the same as a BST because it is a BST. Inserting nodes one at a time now, our worst case complexity for insert still has to be big O of log n, because we know that our AVL tree is always going to be a height that's logarithmic, right? So the worst case complexity for insert is that, and if I want to perform an inner traversal, that's still linear, it's just a tree. So all of the things that we've loved about the BST are still with us in the AVL. All of the good parts of the BST are still good. Let's talk about this insert though. Say, well, I know how to insert into a BST, but I have to keep this AVL tree height balance property going on. So let's make sure that we understand that, because if that's too much work, then it's not worth it. So we start with just inserting like a BST. Then we're going to do this rearranging the tree to balance the height. And it turns out that these things we call rotations are going to do a constant amount of work that just involve moving around 3 pointers and 2 nodes, and that can take any newly unbalanced AVL tree and convert it to a balanced AVL tree. So it's important that it was balanced before the insertion. It was balanced before the insertion. That insertion caused the imbalance. Then with one rotation and a constant amount of work, we can fix it. We can make it be balanced again, right? The way we do this is every node has to keep track of its height. So we've got a little bit more information that's being passed on now. And it's easy to figure out how height works because we don't have to look through the entire tree. At insertion time, I know that I've just inserted some leaf. That thing has to have a height 1. And then it has to know who its parent was because its parent said insert you here. So that node can pass back to its parent. By the way, my height is 1. The parent can then check its other child and say, well, what is your height? If your height is greater than 2, we've got a problem. If your height is 0, 1, or 2 in the other child, since every node knows its height, you can just take a node and ask both of its children what its heights are. So as we do this insertion, a leaf node comes in with height 1, it sends it up to the parent looks to the other side and says, hey, what's your height? If your height is 1, 0, or 2, we're okay, but if it's 3, then we got problems. All right, We need to get something fixed there. So since every node can ask its children what their heights are, every node can compute its own balance factor. So the balance of some node is equal to the height of its left minus the height of its right. Okay, so sometimes this is going to give us a -1, a +1, or a 0. And all of those are what AVL trees consider as balanced. A -1 means that the right side is taller by 1, a +1 means that the left side is taller by 1, and a 0 means that both of the trees are the same height. All three of those things are considered balanced in AVL land. It's only when our balance goes beyond that, when we've got a +2 or a -2, that we say it's out of balance. And we never get beyond +2 or -2 because every time we do an operation, we fix it right away. So if it's perfectly balanced 0, 1, or -1, one more insertion can only take us to -2 or +2 if we're going to be out of balance. Here's our balance factor example. Look at this. There's a couple of trees here. We've seen these two, at least the one on the left, 5 with the children, 2 and 3 on the left, and 7 on the right. So we're trying to figure out how to do balance factor. And when you get started, the easiest way to do this is to first figure out what the height of each node is. So I'll go through and find out the height of my leaf nodes. There, of course, that's 1. The height of this internal node 2 has got a height of 2. I see that 7 is a leaf node height of 1. Now I can figure out what 5's height is by taking the heights of its children, the maximum there, adding 1, says the height there is 3. Great. Now that I've got the heights in, it's easy to go back and set up balance factors. We mentioned that all leaf nodes have a balance factor of 0, so that's good. How about this node 2? We see that this node 2 has a 0 height on the left and a 1 height on the right, so that ends up with a -1. And then that's balanced, that's okay. On the other side, I can see that 7 as a leaf node is balanced, so it's got a balance factor of 0, no children. And then finally, I'm going to calculate 5's balance factor by subtracting the 1 height of 7 from the 2 height of 2, and that just gives me a +1 there. So that's a perfectly balanced tree. None of the nodes in it have a balance that are greater than 1 or less than -1. On the other side, we'll fill in some heights there. Let's just tag both of our leaf nodes with a 1. We move up the tree there. We can see that the height of 2 is now 3, and the height of 5 is now 4. Only thing we've done here is added a 4 below the 3 from the previous tree. With our heights now in place, it's easy to come up with balance factors. I'll take, once again, my leaf nodes, set them equal to 0 because a balance factor of a leaf node is always 0. I move up the tree here. I see that 3 has a -1 balance factor. That means there's a taller right-hand side than left-hand side. There's a 0 left-hand side in this case, but the right-hand side is taller. Negative balance factors mean that there's more in the right. Positive balance factors mean there's more in the left. All right? So as we move up the node, we see that 2 now has a -2 balance factor. It's got an empty left-hand side and a 2 height right-hand side, so 0 minus 2 is a -2. As we work our way up the tree, we see that 5 has a 3 height left and a 1 height right, so that's a +2 balance factor. Both of those nodes are now out of balance. So I've got a non-compliant AVL tree. The height balance property has been violated. All right, do this again. A tree on your own here. I'll give you about 30 seconds. Take a look at this thing, draw it out on paper, put the balance factor on each node. As I mentioned, when you first get started, the easy way to do this is to first draw out all the heights, and then you can go back and do the math on the heights while they're on the page and do that. If you want to skip a step like I always did in math class, you can imagine the heights in your head and just write the balance factors everywhere you see them. So, 30 seconds, let's go. All right, hopefully you've got a bit of a feel for this now. We certainly know that all of our leaf nodes, all our external nodes have a balance factor. That's of 0, so that's great. I can put the 2, the 4, the 13, the 17, and the 20. All of those have a balance factor of 0. How about that nice little complete subtree that's rooted at 3 and goes down to 2 children at 2 and 4? That's balanced. Same thing with a subtree that's got 18 as its root. That's balanced. How about that subtree that starts at 7? That looks balanced. It's a new 2-node tree, a root and a single right child. 6, is that balanced? Well, it looks like it. The left subtree height 2, the right subtree height 2, so 6 is balanced. And then the only node that remains now is the 15. It's got a left subtree height of 3, a right subtree height of 2. Balance factor is +1. Life is good. All right, so let's do this insertion. Now that we know what our balances look like, let's do it. As I insert 14, this is just a standard binary search tree insert. I'm trying to insert 14, it's less than 15, so I go left. It's not less than 6, so I go right. It's not less than 7, I go right. It's not less than 13, so I go right again. And that's where I tack on the 14 at the null pointer that is 13's right child. There we go. Now I need to balance this because I've just inserted this 14 and I have caused some imbalance. Previously, we just analyzed this tree without the 14, it was balanced. But as I work my way up from where I inserted, 14 is balanced, it's a leaf node, no problem. 14's parent in this case is also balanced, no problem there. 13 is balanced, but 7 is not balanced. 7 has a left subtree height of 0, a right subtree height of 2. It's got a -2 balance factor. 7 is out of balance. If you look, kind of turn your head a little angle like this, you can see that the difference between that 14 and the 17 or the 20 on the right hand side of 15 is got to be 2 as well. So I've got an imbalance at 7. 6 is balanced, but as I move up, 15 is also unbalanced. So we have to be careful making sure that we manage this. Turns out that on an insertion, one rotation is going to be enough to rebalance what's going on. On a removal, you may have to do more than one rotation to fix that. All right, and we'll talk about that in a bit. But here, I've got my insertion. This is what the tree looks like. This is a perfectly good BST, a failure as an AVL tree, though. So we're going to have to take these 2 unbalanced nodes and fix them. And because this is on an insertion, I can do this fix with just one rotation. Here's how rotations work. Rotations are going to rebalance the tree by swapping one node with one of its children. We have to preserve the BST ordering, but that swap is going to allow us to balance the tree out. It says here at the bottom, rotation is a local change involving only 3 pointers and 2 nodes. So this tree we have on the left here, 5 with 2, 3, and 4 in its left subtree and 7 in the right subtree, is clearly unbalanced. We've seen it before. It's unbalanced. How do we fix it? We're going to do a rotation, and it's going to end up looking like the tree on the far side. So now 5 is pointing at the 3, and the 2 and 4 are below it. That's good. I've still got a binary search tree. And I've also got a balanced tree. 5's left subtree height is 2, right subtree height is 1. Life is good. What happened there? Look, we've changed, what is that? Swap a parent and one of its children. So 2 used to be a parent, and 3 used to be a child of 2. If we swap those 2 things, now 3 is the parent, and 2 is the child, right? Some Star Wars reference going on here. It's in my head. Search your feelings. You know it to be true. All right. We use rotations to rebalance this binary tree. You're going to interchange the role of a parent and one of its children, preserving the BST property. The second part, preserving the BST property, that's the tricky part. So here's how it is in 2 very terse, hard to parse sentences. A right rotation, that's where we copy the right pointer of the left child to be the left pointer of the old parent. It's a snap. The left rotation is where we copy the left pointer of the right child to be the right pointer of the old parent. Easy. Huh? All right. Maybe not so easy. But it's a whole lot easier to see than it is to read. So we'll see it, and then you can go back and reread it, and you'll say, oh yeah, that's exactly what it said there. So here's what my rotate right looks like. And I'm going to, in my rotate right, I'm going to say that the notation that I use here is rotate right around the parent. So this would be written up as RR with P in parentheses there, because P is the parent. I've got this left child there. That's what's going to be my replacement. When I do a right rotation, it's the left child and the parent that switch positions. So the left child becomes the parent, and the parent becomes the child of the old left child. All right, so the parent goes down to be a child, the child comes up to be the parent. I've got 3 other triangles drawn underneath here. Underneath the left child, I've got this child less than subtree, or the left side subtree. I've got this child right side subtree. So the child left subtree is the gray one, the child right side subtree, that's the magenta one. And then finally, I've got the parent right side subtree, that's the purple one. Evaluating these trees first is important. Let's figure out what's in them. The smallest values in this tree have to be in that gray triangle. They are the leftmost triangle. The largest values have to be in the purple triangle. That's the rightmost triangle. Those magenta items have to all be both less than everything in the parent right subtree and not less than everything in the gray tree. So it's kind of got to stay in the middle there. After the rotation, we see that the left child has gone up and the parent has come down. So where does the magenta tree start at? We see that the magenta tree here starts to the left of the parent. It's to the right of its subchild, but it's to the left of the parent. So as long as that magenta tree doesn't end up to the right of the parent, we're in good shape. Where does that magenta tree end up? Start out in relation to the left child? Well, it's also to the right of the left child. So as long as that magenta triangle ends up to the right of the left child and to the left of the parent, it has to be okay. We have preserved our binary search tree property. And you can see that if you examine the tree now, the parent goes left to the left child, and then we see those 3 trees there. If we swap those two, the left child and the parent, we see that the child right subtree is still to the right of the left child, and since the child right subtree came from the parent's left child, it's still to the left of the parent, and that's good. So we've preserved our BST property here, and we've changed where those 2 items are. The rotate left on the far side is just the mirror image operation of this. We're going to use that similar notation where rotate left says the node that is the parent is the one that's going to be, the rotation is going to be called upon. So rotate left around P is how we might say that, right? So that rotate left, what that does is it pulls some stuff up. You see how it's pulled that right child up. So at the very least, something from the right-hand side has been pulled up. So we're going to do these rotate lefts when we've got too much on the right. It pulls something from the right over to the left. And we're going to do these rotate rights when we've got too much on the left. We're going to pull some stuff back that way. So when we've got a balance factor of +2, that means we've got more stuff on the left than we should have. We're going to pull a rotate right. When we've got a balance factor of -2, we're going to pull a rotate left because that's going to pull some stuff back over there. All right? All right, now let's pull this down to the node level and really take a good eye on this one. Use the rotation to balance these 2 trees. Remember, we have to maintain our binary search tree property, so the values that you see in them, A, B, and C, are actually in binary search tree order. So if I had a binary search tree, A would be less than B would be less than C. That's a BST. It is not an AVL. And the second diagram there, we've got A, which is less than C, which is greater than B, so that's a perfectly good BST as well, just a bad AVL. So how do we use rotations to balance this? I see here that my imbalance in the first tree is at A, so my rotation is going to be around A. That's great. Was it to rotate left around A or is it to rotate right around A? Well, A's got a left subtree height of 0 and a right subtree height of 2, so it's got a -2 balance factor. And when I've got a -2, I need to crank some stuff back over to the left. That makes this a rotate left around A. How about the other side over there? Well, not a whole lot different. It's shaped a little differently, but I can see that the imbalance is still at A. It's got a left subtree height of 0, a right subtree height of 2, so it's a -2 balance factor. So that means I'm going to rotate left around A as well. Let's see how that works out. Well, if I first make this rotation left around A from the first subtree, A goes down, B comes up. Those two items swap position. The parent becomes a child, the child becomes a parent. And that gives me a nice balanced tree. B is now the root, A and C are its children. Life is good. In the second one, it's a little bit harder to manage because I've got what we call a zigzag. And a zigzag is when you have a sign change in your balance factor. So the balance factor at A here is a -2. Okay, we got that. Left subtree height 0, right subtree height 2, -2. How about the balance factor at C? The balance factor at C now is a +1 because it's got a left subtree height with that B node of 1 and an empty right subtree. So it goes -2 at A, +1 at C. So I've got a sign change there. This first one, I've got a -2 at A, I've got a -1 at B, and then I've got a 0 at C. So I don't have a sign change there. It goes from negative to 0. Here I go from negative to positive to 0. So that sign change gives me what we call a zigzag. When I've got a zigzag, I cannot fix this with a single rotation. So we thought early on that A had this -2 balance factor, so I would just rotate left around A. If you take this one and do that replacement, right? I swap A to be the child and C to be the parent. Well, C would be the parent, A would be the left child. Where would B go? Because C already has a left child. Well, that B is greater than A. So I would go from A, C, B after a rotation left, and I'd have reversed a zigzag. So I'd have C at the top, A, B. So a single rotation when you've got a zigzag will not work. The ultimate rotation that you described still has to happen. We said that this has a -2 balance factor, so I will be rotating left around A, but I have to do an intermediate step when I've got a zigzag. And we see here that this rotate right around C is the intermediate step. It takes my zigzag and unzags it. So A, C, B, if I rotate right around C, gives me that stick tree that I was looking at earlier that goes A to B to C. Then I can rotate left around A like I always knew I would. This double rotation involves me doing an intermediate step there. I rotate right around the sign change. So it was -2, +1, 0. I rotate right around the +1, and that gives me -2, -1, 0. And then I can rotate left around A. It's just going to give me a 0, 0, 0, 0. I'm completely balanced. So that's what the rotations do. So sometimes we have to do a rotation. Sometimes we have to do a double rotation. And before this gets too crazy, a double rotation is what it sounds like. It's 2 rotations. Okay, so if you're ever counting the number of rotations, a double rotation counts as 2 rotations. All right, good enough. So as we do an insert, we end up with these 4 cases. I may have to do a single left rotation. I may have to do a single right rotation. Those are pretty easy. Those are when I have no sign change. A single left rotation is when I've got a -2, -1, 0. A single right rotation is when I've got a +2, +1, 0. A double rotation right-left is right rotation first and a left rotation following. So here's when I've got a right-left, which looks like I'm going to go right with my zigzag and then left. So I'll rotate right and then rotate left to fix it. Okay, so I can say that this one has a balance factor that looks like -2, +1, and then 0. That's how this double rotation shows up. This double rotation here is one where I'm going to go left first on the child and then right on the ultimate problem. So that's going to be something that's got a +2, -1, 0 balance factor set. This is another set of illustrations that show this out very nicely. I like this particular version because the triangle heights that show that there's some subtree there, those triangles represent some subtree. But what's important about these is that they're actually drawn to scale. So we can see these triangle subtrees, T0, T1, T2, and T3. They are of the heights that are shown there. And then the nodes that are important are actually illustrated, A, B, and C. So there's where we're going to be dealing with our rotation. You can see that I've got an imbalance at A. The height difference between the bottom of T0 and the bottom of T2 is more than 1. I've got a problem there. So I'm going to rotate left around A to fix it because I've got a -2 balance factor. So I rotate left and A goes down, B comes up. A becomes the parent of B. B becomes a parent of A becomes a child of B. But looking at the diagram, you see that B already has 2 children. So how can I make A be one of B's children if B already has 2 children? Well, we've got to do this handoff, and that was what was in the tricky statements earlier. I have to do something with that T1 because I'm going to make A be B's left child. So T1 has to go somewhere. Where should it go? If you look at the diagram, you see that everything in T1 is greater than A because it's in A's right subtree. So if I promote B to be A's parent, and then I set A to be B's left child, the only place that I can put T1 and protect my BST property is as A's right child, which just got freed up, by the way, because it used to be B and now it's not. So you can see that that T1 has kind of been thrown across. That's why it's got that shading in it. T0, T2, and T3 are all exactly attached where they were before the rotation, but because A and B need to swap and there may be some children in B's left subtree, that T1 has to get passed back to A. And then that's what happens after the single rotation on the far side, and you see that the bottoms of those T0, T1, and T2 are all level, and there's only a 1 child step difference there between 2 and T3, which means all of A, B, and C are balanced, and as long as T0s through 3 are balanced, this entire thing is balanced. The one on the bottom is just the mirror image. That's a single rotation. That's a rotate right around C. Same thing, I've got this tiered going from T1 to T2 to T3. That's a balance factor of +2 for C, so we're going to have to rotate right around C. And to make that happen and protect our BST property, we've got to pass T2 over to C. All right? So this is what I said here. In a right rotation, we copy the right pointer of the left child to be the left pointer of the old parent. When the left child has a right pointer already, in a right rotation, the left child is going to become the parent, and the parent is going to become the right child. But if the right pointer of the left child is not a null pointer, we have to pass that off to be the left pointer of the old parent. That's where the handoff is. And then the bottom one is just the mirror image of that, copying the left pointer of the right child to be the right pointer of the old parent. All right, say that 5 times fast, and you will get it. This is a diagram of my double rotations. This one is the first rotate right, rotate left version. And if you look in the diagram there, we've got the zigzag in place that goes from A right over to C and then zigzags back to B. So the balance factor at A is a -2. The balance factor at C is a +1. I've got a zigzag. The difference of A's children is 1 and say 3, so it's definitely a negative 2 balance factor at A, so I am going to end up rotating left around A, but if I do it first, I'll just end up with this mirror image, the double rotation. With the single rotation on a zigzag, I just get the other zigzag. So the first part is to rotate right around the child. I'm going to rotate right around C, which then stretches things out even farther here. We see that T0, T1, T2, T3. Now I've got A looking even worse than it was before because I'm looking at this balance factor of being off as 4. But when I do a balance, when I do a rebalance that's a double rotation, I've got to identify the fact that I have a zigzag before I get started, right? I'm figuring out what my balance factors are. I find there's a 0 at B, there's a +1 at C, there's a -1 at a -2 at A. Okay, I've got an imbalance, but it's a zigzag imbalance, so I'm going to have to do 2 rotations before I do any other checking. I figure out what they are, and then I do them back to back. I rotate right around C, which makes things look even worse, but then I immediately rotate left around A, and I get this beautifully fixed AVL tree over there on the bottom with B as the root node and A and C as its 2 children, T0, T1, and T3 all at that similar depth, and T1 just 1 step above that. So that's what the double rotation looks like. The next slide is just the mirror image version. Here we've got the zigzag, which is C going to A, going to B. So I've got a +2 followed by a -1 followed by 0. There's my problem. Okay, so that +2, -1 means I've got to first rotate left, but I will ultimately be rotating right. The +2 means I'm going to have to rotate right. But the zigzag in the middle means I've got to rotate left in there first. So the rotate left as before makes this unbalanced tree look even worse, but I don't check in between the rotate left and the rotate right. I identify that I'm going to do them, and I do them both at the same time, or back to back. All right, this is yet another illustration of this. Hopefully we throw enough pictures at you, you will understand this. That's the goal here. So this is just another version of this. We can see our left-left case. That's my left-left imbalance, which turns into a single right rotation to fix it. I've got the right-right case in the second column, which turns into a single left rotation to fix it. I've got the left-right case, which is a left rotation followed by a right rotation, and the right-left case, which is a right rotation followed by a left rotation. So this is just another version of this, another set of pictures, different colors. You see some different notation styles, but those triangles below say we don't know exactly how tall those things are or how many nodes they are, but they do have the same height. And you can see how the passing off happens when we've got to pass off some triangle to another triangle, and that's the A, B, C, D triangles. The D is always hard to see because it's so dark, but that's a D triangle, and it passes off to where it should be. The nodes are numbered with values that make sense. The root is a 5 here, then the pivot is 3, and then below that's a 2. So this is just another version of these. How does this get done? This is the problem that always shows up here as we try to figure out where this goes. Check and balance. Now, I'm going to check and balance every time I do an insertion. This check and balance says I know where I've done some insertion. I can work my way back up. And the balance factor is something that I remember since every node knows its height. As I do the insertion, it's part of some recursive call. You've gone left, you've gone right, you've gone right, you've gone left, you've gone left, you've gone right. There's your null pointer. Then you reverse that on the call stack on the way back up. And each one of those things can check its balance. And if they're out of balance, we fix them right away. And once that thing is fixed, it's going to fix the balance all the way to the root. Because what happens is on an insertion, you're making the tree 1 taller somewhere. And then that rotation pulls something back up. So one rotation, one rotation balancing, right? So that I get some clarity there. One fix, one balancing is all that's needed upon an insertion. Sometimes that balancing is a single rotation. Sometimes that balancing is a double rotation. But once I do that fix at a single place, I don't have to do any more upon insertion, because as I insert, the tree gets 1 taller in a certain place, I rotate it, and then it pulls that back up, and the rest of the tree was already balanced, and so now we're balanced. So that's why we only have to do 1 balance on an insertion. Now, when I'm doing a removal, that's not the same case, right? On a removal, I could have sort of like a long side and a short side, and since I removed something from over here, I might have to do more than one rotation to get that back up. So upon a removal, we're going to work our way from the removal site all the way to the root to make sure that everything gets fixed on the balance, and we'll talk about it in a minute. So this is check and balance. It's just pseudocode. You can see that as I check the balance at any node, if the balance is greater than +1, then I'm going to be doing a rotate right. Same thing down here. If the balance is less than a -1, I'm going to be doing a rotate left. However, as I work my way through checking for a zigzag, if the balance at n is greater than a +1, I say if the balance of its left is less than 0, because if the balance at n is greater than a +1, the problem is coming from the left-hand side. So I only need to check the left to see if that's got a negative balance. There's my zigzag. If I do have a zigzag, then I'm going to rotate left first, rotate right second, and fix things. The same is true for the mirror at the bottom there. So this is, you're going to do a check and balance as you work your way back out the call stack. When you do an insertion, you recurse down to the insertion point and you check and balance your way back up. So we've got this outermost if that tells us if we're going to do a rotation there, and then the inner ifs check to see if we've got a double rotation set up. If the signs disagree, then we do the double rotate. So as insert finishes, every recursive call updates the height of the current node because it's just added something in its subtree, in one of its subtrees. So you say, well, that thing knows its height. I'm going to ask it and see if I need to update my height. If I need to update my height, my parent may need to update its height, and so on, all the way back up. So as the insert happens, we're going to have to do this check and balance so that we find any imbalances and we update every node's height all the way back to the root. That's how it goes. So complexity of this ends up being what? We're already doing the log n insertion, so we're not paying any extra to work our way back doing a check and balance, because that check and balance was a constant amount of work. We're just checking the balance here, checking the balance there, doing a rotate. We said a rotate is a constant amount of work because it just involves 2 nodes and 3 pointers. So there's a constant amount of work that goes into these rotations, even if it's a double rotation. Now it's just 4 nodes and 6 pointers. That's a constant amount of work. So I'm always going to be doing a constant amount of work to fix something with a balance. And since I'm working my way down log n to do the insertion, because it has to be log n, we've already got an AVL tree, I do a constant amount of work to fix it. It's great. We can say that this hasn't changed the complexity of insert, but it still makes all of the rest of the things stay at log n, which is awesome. So here's our rotation exercise. Insert these keys into an AVL tree and rebalance when necessary, right? The keys are in this order: 3, 2, 1, 4, 5, 6, 7, 16, 15, 14. Below is just a chart that shows the pictures of how those rotations should work if you want to do this and have something to look at. So that's just there for notations. So do these insertions. I'm going to take a sip here and give you a good solid minute. It's not going to be enough time, but it's enough time to get started. See where you have to do a rotation. Do those rotations and get all of these things inserted. There's only one tree that shows up here. We'll get it done in a minute. It's a good thing I got this lecture today. I don't think Dr. P has played with this next slide. It is animation. Heaven? Maybe not heaven? I don't know. It's a heck of an animation. I spent a fair amount of time getting this one done right. So we'll see this work its way out, and then we'll look at some more animations later as well. All right. So it's easy to see that inserting 3, 2, and 1 aren't really a problem, right? It's when I get to the 1, as I check my way back up to the top, I see that I've got an imbalance at 3. It's unbalanced at 3, so I'm going to insert there. So I insert 4, that's no problem. Check and balance to the root, no problem. I'm going to go then and insert 5. 5 gets inserted. We do have a problem at 3, so we're going to do rotate left around 3 and check our way back up to the 2. Things are good. We insert 6 now. We've got an imbalance, but all the way up at the root, the check and balance finds it there, swaps those two things, and now we go back and try to insert our 7. All right, now we've got this balanced tree, and that's me inserting 7. Sorry, there we go. That one jumped, my animation jumped there, sorry. But this animation is just a screen capture from Visualgo. Visualalgorithms.net, visualgo.net. So you can go there and open up binary search trees, make sure you choose the AVL tree, and then you can give it any list of nodes and watch it do this insertion in order. So we can see that those rotations all happened when we needed to. Inserting 3, 2, and 1, inserting 3 into an empty tree is no problem, that's balanced. Even inserting 2 is balanced. It's when we put the 1 in there that we came up to our first imbalance. We fixed that by rotating right around 3. Then we could insert 4, which was no problem. Once we inserted 5, it was unbalanced at 3, so we rotated left around 3 to fix it. This pushed the 3 down, brought the 4 up. We were able to insert 6, which unbalanced things, so we rotated left around 2 to fix that. Then we inserted 7, which gave us an unbalance again. We rotated left around 7. After inserting 16, we were good, but 15 gave us a zigzag imbalance where we had to rotate rotate right, then rotate left. Inserting 14 did the same thing. It gave us another zigzag imbalance, which we fixed by rotating right around 15 and rotating left around 6. Let's see it again. There's the check and balance happening. We insert, it checks its way back up to the root. It says everything's fine. There's a fix. Now as we insert 4, it checks its way back up to the root. Nothing's unbalanced, so we can insert 5. We do that. We jump down. As it checks its way back up to the root, it finds an imbalance at 3, rotates to fix it, continues checking its way back up to the top, no problems. Now we can insert 6. It goes down. 6 gets inserted. We need to check and balance our way up to the top. We find the imbalance at 2. We rotate left there to fix things. Now we can go to inserting the 7. We get down to the 7, check and balance our way up, find the imbalance at 5, rotate for the fix, check and balance up to 4. Things are good. We go and then insert our next value. That's the 16. Checks and balances its way up to the top. There's a problem, no problem, until we insert the 15. Now as we check and balance our way up, we got the zigzag with the imbalance at 7. So we first do a rotate right, then we do a rotate left, and we continue to check our way up to the top. It's good. We insert the 14, which gives us the zigzag below 15. Actually, the zigzag is below 6, right? So we do that first rotation right, then a rotation left, the check up to the top, and we're good. So take those values, go to visualgo.net, and plug them in and try it, or any other values you like. Try to figure out, how can I do this in a way that removal is going to cost me some stuff. So removal is similar to the BST. We've always got our same BST removal. We know that find the in-order successor and replace the node that we're deleting, and we should be good. However, when we pull something up there, we may have made that tree shorter and caused an imbalance. So we have to do another rearrange the tree sometimes to keep that height balanced. So we travel up the tree from the parent of the removed node, right? You start with the node that you're going to take out. Yeah, that's a good point, Dr. B says. Better yet, do it by hand yourself because you won't be able to log in the Visualgo during the exam. All right, so do it by hand yourself so that you know how to do these things. Good practice. So when we do a removal, we're going to travel up the tree from the parent of the node that we just took out because that's where our imbalance could have been generated. At every unbalanced node we encounter, we rotate as needed to fix it, but because we've removed something, we've made the shorter side possibly shorter still, we may have to get our rotations all the way up to get to the root to be able to rotate something back around to get it down there. So with insertion, the first time we do a fix, we're good, but with removal, we have to fix all the way up possibly to the root to make sure that things are good. So this restructuring may unbalance multiple ancestors. You have to continue to check and rebalance all the way up to the root. Can we write a program and use it during the exam? Well, if you write the program, I feel like you've done what I wanted you to do. All right, so here's AVL tree remove. It's same as removing a binary search. I'm going to try to remove this 32 here. So this is a little sparse on the left-hand side, but if you look at it closely, it's still balanced. This is still a balanced tree. When I remove 32 now, I've got an imbalance because 44's left side has got a height 1 and right side of height 3. So it's got a -2 imbalance. We're going to have to rotate some stuff back to the left to fix that. So as I remove 32, I'm going to have to fix that. And so we travel up the tree from the parent of 32. That's the 17 node. Say, well, 17, that's balanced. I don't have to do anything for 17. But since 17 used to be height 2, before it lost its only child, now it's height 1. It can report to its parent, hey, my height is now 1. And the parent can say, well, the height on the other side is a 3. We got problems here. We need to do a rotate left around me. This rotate left around 44 then swaps things over there. And we can see that 62 goes up and takes 44 as its new left child, even though 62 already had a left child, which was 50. That left child gets passed over to 44 to be its new right child. And that is a tree we get on the far side after we've done this. Now we've done this rotation left and we're up to the root, so there's no more checking to be done. But in a deeper tree, you might have to do something there. So this question is, how many fixes are needed after remove? Well, after this remove, there was 1. But after a remove in general, we have to fix our way all the way up to the root because we may find some other things that got unbalanced. Here's another one where we're going to take that tree where we already were and then remove the 62, which is the root. So we have to find the in-order successor. The in-order successor in this case is we jog once to the right and go left as far as we can, which is nowhere. So the in-order successor is 78. We copy the 78 over the 62 and then delete the 78 node, pulls the 88 up, and now I've got this tree that needs to be rebalanced. 78's got a subtree height of 3 on the left, 1 on the right. It's a +2 imbalance. We're going to rotate this thing back to the right to fix it. And not only that, it's got some zigzag going on because 78's subtree height of 2 gives us a +2 balance factor, and 44 has a -1 balance factor. So we've got a zigzag. We're going to have to do a double rotation. First left around 44, which gives us a tree over there on the far side. And then finally, we're going to rotate right around 78, which gives us that tree down there at the bottom, nice and balanced. All right. Rebalancing one or more. I've already mentioned this a couple of times. Here's a slide that should stick this in your mind. A fix, which is either a single or double rotation, right? We don't think of it as rotation. We think of it as fixes. A fix shortens one subtree that is too tall. That's how it works. So when we've inserted and we need to fix, we've just created this problem by making it taller, by adding the thing. So if I fix that and shorten it, then I'm done. When I remove, however, since I can be making the tree shorter than it needed to be on one side, and all that the fix can do is shorten something, that shortening might not be enough to get it. We might have to go up another level till we can figure out where can I rotate this back to fill in what's been deleted. So a shortened subtree is already shorter than a sibling. A fix is needed at a higher level, so multiple fixes may be required on remove. Only one fix needed on insert. So here's an example of a tree that's going to show you The values 1 through 33 are inserted into this AVL tree in some order. You can go through and try to pick out what that order is. The resulting tree is balanced. I'm going to remove 4 here, and that's going to shorten up 3 and cause a problem at 3. As I fix 3, all it does is pull more stuff up because it's a fix. Right? Well, that creates an imbalance at 5. So I'm going to have to rotate around 5 to fix things. And now I've still pulled things up. That's all fixes do. And so I'm still unbalanced at the root. Now I can get to the point where the root can be pulled up. And now we've pulled up the long side on the right. And so there's an example of one removal requiring 3 rotations. Or sorry, not 3 rotations, 3 fixes to build this. So this is once again animation screen capture from visualgo.net. But this is a great example of how more than one fix may be required when there is a removal. Check out Visualgo. You click on AVL tree near the top. You can insert and remove several nodes one at a time, slow them down, speed up the demo. There's comments about what's happening. You can turn those on and see what's happening while it's going on. You really understand what's going on in these things. All right, it's time for my summary slide here. We talked about binary search trees. We know that their worst case insert or search is linear because we can have sticks. AVL trees are BSTs that have this height balance property that prevents the worst case from ever getting worse than the big O of log n. The operations search, insert, remove, and sort are all sort of predicated on that height. So when we keep it at log n, we end up with log n for search, log n for insert, log n for remove, and sort. I can do 2 times log. Wow. I can do an n log n because all I have to do is build the tree in these log n insertions. I stick all n things in there, paying no more than log n work for each one of them. I end up with n log n to build the tree, and then I can do a linear time traversal in order to give me that sorted data. So I can use a binary search tree to do my sorts in n log n, which is our theoretical sort maximum speed. A rotation, we talked about those things as how we did fixes. It's a constant amount of work for a single rotation and a constant amount of work for a double rotation. All right, minutes before lunch. Let's go get it. All right, we'll see you in office hours after food.